In this section, we're going to look at evaluating some integrals, but they're going to look a little bit deceptive at first. This is a class of integrals which are known as improper integrals, and they are most visible when you have an endpoint that is infinity. And you might be thinking, if you're calculating area under a curve, how in the world could one endpoint be infinity and the total area not just be infinity? Because you're just continually adding more and more area as you do that calculation. Well, it turns out under certain conditions, these types of integrals can exist, and we'll explore those in this section. There's another case, however, that's not quite as visible, but certainly under the same circumstances, really. If you have a point on an interval that results in an infinite discontinuity, so if you have a vertical asymptote, which means that the function is running off to positive or negative infinity in the y-axis, then you also have a improper integral. And so we'll look at how to deal with both of these cases, but we'll start with improper integrals of the type that have an endpoint at infinity, because that's usually the most visible and the easiest for students to kind of wrap their heads around. So how can these things possibly exist in the first place? Well, consider an integral of this form right here. So I have some integral of the function of a function f of x integrated with respect to x on an interval from the value a up to infinity. So infinity is not a number. You can't just plug infinity into a function and it make any sense whatsoever. It absolutely doesn't make any sense. So what you can do, however, is you can look at what the value of the function approaches as you let x get larger and larger and larger. And so that's the way we have to approach this as well. So we have to consider an integral of the form f of x integrated with respect to x from a, the starting point, which is non-infinite, to t, so a finite value. So it could be from a to 100, then a to 1,000, a to 10,000, and so forth. And as that upper endpoint gets larger and larger and larger, you can kind of observe through the different values of the integral, and making those observations, you can then decide what the value of the overall integral is approaching as you let the upper endpoint go to infinity, which effectively makes this a type of limit. So, in order to evaluate an improper integral, here's what we'll do. So, let f of x be continuous over an interval of the form from a to positive infinity. So we have some function that's just fully defined everywhere on this interval. So we can observe what's happening to it. All right, then the integral from a to infinity of f of x dx is defined as, so we calculate this function, we calculate the value of this integral, I should say, as the limit as the upper endpoint goes to infinity of a to the upper endpoint of f of x dx. Now, that limit may or may not exist. So it's entirely possible that the value of this limit is just infinity. So in that case, we would say that the limit, the integral diverges. But it's entirely possible that this limit actually does exist. And if it does, then we say that it exists, or the value of the integral exists, and it is equal to that limit. And it's entirely possible that we might be dealing with an interval that's actually going from negative infinity up to some finite value. And we can do the same approach here as well. We just let the lower endpoint, which is negative infinity, approach negative infinity using a limit instead. So it works just the same. Or you can be doing this on an entire interval from negative infinity to positive infinity, for which case you have to break this up into two separate limits, one going from negative infinity up to some point in the middle, which 0 is kind of the easiest one probably to use, and then going from that point up to infinity, and then basically doing the first two cases separately. In any of these cases, however, if the limit does exist, then we say that that improper integral converges, and converges to the limit value. If the limit does not exist, then the improper integral is said to diverge. So let's take a look at evaluating one of these and really see and understand what's happening. All right, so I have an integral from 1 to infinity of 1 over x squared dx. Now, the first thing that we will do in this process is to rewrite this as a limit. And when I say the first step in this process is to rewrite this as a limit, I do very much mean that. So if you want to make sure you get some points off, or some instructors don't give any credit at all, if you don't write this as a limit, then make sure you don't write it as a limit. However, if you want to make sure you do the problem properly and get full credit, step 1, write it as a limit. So we write it as a limit as t goes to infinity from 1 to t, and we're integrating 1 over x squared. Looks like we could probably integrate that using the power rule if we wrote this as x to the negative second power. I'll go ahead and do that. Now, the first job here is to evaluate the integral that is here. So we'll just evaluate this integral as is. It's okay that the upper end point is a variable. The fundamental theorem allows for that as well. After we get a function for this integral, then we will handle the limit portion of this. So we'll always do the integral first and then the limit portion. So let's start with this integral. For the time being, we just need to drag along this limit, or if you want to go off to the side and do the integral separately and bring, the value of the integral back, that's fine too. But this integration is pretty easy. If we integrate x to the negative second, we would add 1 to its exponent by the power rule. So x to the negative first, and then divide by that new exponent, and then that's going to get integrated, or evaluated, I should say, between 1 and t. I think I'll just go ahead and pull the negative outside of the limit, just so it doesn't get in the way. All right, so this is just 1 over x, and I guess I'll take an extra step for that, just so you see exactly what I'm doing. All right, so negative limit as t goes to infinity, and this would be 1 over t minus 1 over 1, which is just 1. I think I'll just write that as 1. And let's see what happens. So now we have a function that's come from our integral. We want to see what happens to this function as t gets very large. Well, as t goes to infinity, 1 over t, the value of that goes to 0. Okay? And I have this negative. The value of a constant just stays constant through a limit, so that's fine. So 0 minus 1 is negative 1. So evaluating that limit, I get the opposite of negative 1, which is positive 1. And what that tells me is that the value of this integral from 1 to infinity of 1 over x squared dx results in 1. So if you think about that, if you think about the graph of this function, right, so 1 over x squared on this interval, of course, 1 over x squared has an asymptote at 0, and then basically looks something like this. Okay, but we're just on the interval from 1 to infinity, so I'm just going to ignore this part of it because that's not on the given domain. So 1 perhaps is right here, and we're looking for the total area from 1 out to infinity. And what we've just discovered is this area happens to be a finite amount of area and is equal to 1 unit. And the mathematics supports this, but perhaps the logic doesn't. And you might want to stop and think about that for a minute. We have a region here that is infinitely defined. So it goes to infinity. And yet the total area of this region is finite, which is 1. It's very paradoxical. If you aren't able to wrap your head around the concept, I don't blame you. Sometimes I get a little bit befuddled by the concept myself. But it's an entirely true fact. All right, so we've proven it through the mathematics. Let's look at another example. Very similar, but this time we have to evaluate the integral from 1 to infinity of 1 over x with respect to x. Okay, first step is going to be the same. We need to change this thing into a limit, because we can't just plug in infinity as a value. We have to observe what happens to a function as we let the value of the function approach infinity. So we'll change the upper endpoint to t, and using the same idea here, I'll go ahead and change that into x to the negative 1 power, although if you recall, this doesn't actually get evaluated. The integral doesn't get evaluated using the power rule, because if we add 1 to this exponent, it goes to 0, and then divide by the new exponent, we get division by 0. If you'll recall, this is actually a natural logarithm. So this is the limit as t goes to infinity of the natural log, and it's technically the natural log of absolute x, but all of my values are from 1 to positive infinity, so those are all positive anyway, so we don't need to worry about the absolute value in this case. Okay, so now I am evaluating the natural log of x from 1 to t, so it's going to be the limit as t goes to infinity of the natural log of t minus the natural log of 1. And if you'll recall, the natural log of 1 is a known value. It's one of the few values that we can evaluate logarithms at and get an integer answer. And that happens to be 0. Okay, so then the natural log of t, as we're letting t go to infinity, this function, the natural log, goes to infinity itself. Because if you think about the graph of natural logarithm, it's got this asymptote at 0, has the point here at 1, which is at 0, but it just kind of slowly increases as you go to infinity. So it's getting larger and larger and larger in value. So the value of this function as t goes to infinity is infinite, which means the value of the limit is infinite, because infinity minus 0 is still infinity. So that means that this function, its integral diverges. All right, now this graph pertains to the natural log function. To bring it back to the original, so the original graph here, 1 over x, kind of looks the same as the previous one. 1 over x doesn't look a lot different than 1 over x squared. And you can even see that on your calculator if you were to graph both of them together on the calculator. So 1 divided by x squared, if you graph it, that's what it looks like. And you know what? I just realized I said that there was a portion in the negative part down here of x squared, but obviously that gets flipped and becomes positive x squared. Doesn't change what happens on the positive part where we were, but I do apologize for that, that error. Now, comparing that to 1 over x. It doesn't look much different from 1 over x squared, okay, on this interval from 1 to infinity. But here's the thing. This region from 1 to infinity, for the integral of 1 to infinity of 1 over x dx, it diverges. It's infinity. But for 1 over x squared, it converged to the value 1. So that is even more perplexing, I would assume. Wouldn't it make sense that if this region were finite, that it would follow that this region would also be finite, because it's not that different ultimately. And, well, what happens here is whether the integral exists or does not exist depends not only on the function going to 0, but also how quickly the function goes to 0. So the function 1 over x doesn't go to 0 as fast as the function 1 over x squared. Let me go back to the calculator and try and show you that. So if let me make the window larger, and I will just kind of change the window so we're only looking at the portion that we're really interested in here. So from 1 to 10 on the x, and I'll just set the scale to 1. And I don't think we need this that high. So let's say from negative, no, actually let's say 0 on the y min and positive 2 on the y max. All right, so in blue, we have 1 over x squared. Look how quickly it's dropping down to 0. In red, we have 1 over x. It's definitely not dropping to 0 nearly as fast. So that's the difference. It's how quickly you go to 0. And it turns out that 1 over x is kind of like the speed limit. Essentially, whatever function you're looking at, it has to go to 0 faster than 1 over x in order for it to converge. All right, not really a hard and fast rule, but definitely a good guideline that you can kind of think about and wrap your head around. So as long as a function's going to 0 faster than 1 over x, it will ultimately converge.